Now let's discuss solute diffusion in a thin planar membrane. So our goal to obtain BE is the effective diffusion coefficient in the membrane. So this is the membrane we are looking at. It has a thickness we call L bar, and the area is S, and there are holes in it, pores in it. So we assume the pores have circular cross-sectional area cylindrical pore and of radius circular cross-sectional area like radius of R. So in order to get the effective diffusion coefficient in the membrane, let's divide the process into multiple steps. First, let's consider solute diffusion in a single pore, not the membrane. Solute. In a single pore, that means we zoom in a pore. Both sides of the pore is off. And we consider the starting point is x, for this x-axis. The mouth, the entry of the pore is x equal to 0, and the other mouth of the pore at the exit is x equal to L bar. And the pore has a radius R. Let's consider steady state. One-dimensional diffusion. That's the So basically, if you have solute needed to be transported from one end of the membrane to the other end of the membrane, then those solutes needed to go through the pore. And that's where the diffusion happens. And that's along the x direction, which is also the axial of the cylindrical pore. Since now for this problem, whenever you wanted to solve a diffusion problem, you always want to start with fixed second law. So fixed first law give you the flux. Fixed second law give you a governing equation. So use fixed second law, which tells partial CA. Now it's in the pore. Now we are modeling our diffusion within the pore region. Partial C at the pore equals to the diffusion coefficient of the pore would be in the pore multiplied by the Laplacian of the concentration in the pore. At a steady state, go to 0. And also it's 1b in x. It means the Laplacian becomes b squared, bx squared. So with this, our governing equation becomes this one. B squared CA or squared equal to 0. If a second derivative of a variable is 0, it means this quantity is linear in X. Now let's set well, since it's linear in X, you know a linear function would you have to like constant to solve to fix. So basically you know that CA4 equal to C1x plus C2. And the C1 and the C2 are determined by boundary conditions. So now the boundary condition refers to what happens within the pore. So the boundary conditions BC1 at x equal to 0, we say CA4 equals to CA4 at x equal to 0. You may wonder, what does that mean? We still don't know what is CA4 at x equal to 0. We just give it a symbol annotation. That is correct. At this point, we don't know what its concentration because it depends on the exactly like physical, biophysical problems. We don't know, but right now we use it as a placeholder. We just say at the boundary, if this is this concentration, let's just give it a name. Let's call it CA4 evaluated at x equal to 0. Similarly, with BC2 at x equal to L bar, CA4 equal to CA4 evaluated at x equal to L bar. So in a lot of physics and engineering problems, when you solve those generic equations, it's okay to use placeholder. And usually those placeholders will be figured out later on when you get more information. And we will have a number of scenarios in later sections down the like in a later part of this course. We do need to solve some problems that we needed to use a placeholder at the beginning, and then we figure out what's a placeholder. Sorry, placeholder. And then now we just use these two symbols. Now with these boundary conditions, we can solve for our solute concentration within the pore as a function of x. As this one of CA4 x equal to 0 minus CA4 x to 0 minus CA4 at x equal to L bar divided by L bar multiplied by x. This is the solute concentration profile in a pore. Okay. So now if you want to find the flux, so the flux means so this is the flux in AX. Let's find the flux within the pore. So we are going to use first law to find the flux along the x direction. Is NAX, which is in the pore for one pore. It is minus D4 B concentration That's so you can take the derivative and since it's linear, so it's easy to take the derivative. It's just that this coefficient which shows the gradient. Then it give you the pore multiplied by CA4 x equal to 0 minus CA4 x equal to alpha divided by alpha. This is the flux. Now in practice, the solute concentration within the pore is often not measurable. So here you can see we write it in terms of the pore. So what it means is the concentration within the pore at the two ends. And it's not so easy to measure it because if you think about what it is part of the membrane. And the membrane is those small gaps and the pores within, for example, an endothelial wall, a vessel, blood vessel wall. So there is no way you can like stick a sensor into the tiny spaces between the endothelial cells and measure like what's the concentration. That's impossible at least at this moment. Maybe in the future you create some interesting device that you can do that. But now it's not something it's so easy to measure. And in general, even if it's not for a transport across the blood vessel, even for some like larger scale biomedical devices or other applications, usually it's still not so easy to measure the concentration in the pore, in the membrane. So however, what can be measured is the concentration outside the bulk part. That can be measured. And if you wanted to express the flux in terms of the bulk concentration, we can do that. We just use the partition coefficient. Use partition coefficient we discussed in the last lecture. So we know K equals to CA evaluated the pore mass divided by CA evaluated at the bulk mass. This is evaluated bulk. Both are taken at the pore mass, this location. So that means we can rewrite our flux in the pore in terms of the concentration in the bulk. That is a more practical for people to connect to what can be measured. Okay, that's nice. Also, to account for the structural complexity of the pore, two further modifications are going to be made. So first, we consider the tortuosity. We also discussed this tortuosity in early lectures. Now consider the tortuosity. Tortuosity of the pore. So the pore, if it's straight, then the length would be the thickness of the membrane. But sometimes you may have a pore which is a little bit wiggled. And this is length L or length L bar. But the true length of the pore, this is the true length of the pore, which is longer than L bar. So the true length, true pore length would be a coefficient between the tortuosity multiplied by L bar. So we are going to consider this. So this is the first thing we are going to consider. Second, we are going to consider the hindered diffusion we discussed also in the last lecture. It's due to the hydrodynamic inaction. So the hindered diffusion within the pore reduces the effective diffusion coefficient compared to the bulk part. So in the end, in the hindered effect, you give it a symbol omega r. Omega means a factor which is less than 1. It's all equal to 1. The tortuosity is always large or equal than 1. So the hindered impact means how it reduces the diffusion coefficient because of the inaction. So we consider the hindered impact is a correction by the bulk diffusion coefficient. So the impact, the hindered impact makes a correction from the bulk diffusion. From the bulk diffusion coefficient. DAB is the bulk. So actually when we say D4, it is, we are actually means DAB multiplied by omega r. So considering the tortuosity, and also we introduce the omega r, now we can rewrite our pore, flexing the pore in terms of alternative symbols. So now we have DAB, then we have K omega r divided by tau, and then we have CA or evaluated at x equal to 0 minus CA log evaluated at x equal to L1 divided by L1. So this is our new notation. And this sometimes we put dm. So dm is they call it membrane. It's not necessarily the effective diffusion coefficient of the membrane. It is the diffusion coefficient of a pore in a membrane. So this is diffusion coefficient in a pore added in a membrane. So this is our discussion the solid diffusion in a single pore. Now let's figure out the effective diffusion coefficient of a thin planar membrane. Now let's consider the entire membrane. That means you have many pores, not just one pore. So effective coefficient of a thin planar membrane. So now let's consider, let's draw again. We have a membrane of area S, and we have pores. So the total area of all pores we call the AP. This is exactly the same notation in early lectures when we discussed hydraulic conductance of a membrane. So we use the same notation. So we can also define a membrane porosity of epsilon equals to AP divided by S. So if you are asking what's the flux across the entire membrane, so solute flux across the membrane, not a single pore, so NAX. This is determined by the porosity. So it is a ratio of all the area of the pore divided by the area of the membrane and then multiply the flux through a single pore. And think about that the flux through a single pore is how much flux you would get if you have a void space. So the entire pore is well you would expect a solute to transport. But if you have a membrane, now the entire membrane isn't totally void or permeable. Like you only have a fraction, the porosity epsilon, only have this fraction AP divided by S, which is in a void space. So that then if you consider the total flux, it's the ratio between these two areas. Another way you can look at it is you think about the flux per unit time. So if you have S multiplied by NAX, so the surface area of the membrane multiplied by the flux across the membrane should be the same as the total area of all the pores multiplied by the flux through the pores. So this should be the same. So you can also derive NAX from these values. So you plug in the expression for what is the flux in the pore. We get dAB multiplied by AP divided by S multiplied by K omega R divided by tau. And you have another term. X. Okay, now we have this coefficient. This is the effective diffusion coefficient of a thin planar membrane. You want to write it in terms of the porosity, you can use epsilon. And again, K is the partition coefficient, omega R is the hindering factor, and the tau is the porosity. So this is the effective of the membrane, and maybe that's the better way to say it, of the membrane, of the thin planar. Okay, so that's it. That's we derive the diffusion coefficient. Now you think about how interesting it is. We can just by exploring the geometrical factors, and all the factors, and also think about it to connect the flux, like within the pore versus from the bulk part. We can get this if the membrane. Now, whenever people give you a piece of membrane, so for example, if you are going to work in the biomedical industry or any industry that uses semi-permeable membrane to filter something, someone hand you a membrane, and as long as they give you the geometry of the pores in it, the total area, whatever, then you can tell what's the diffusion coefficient of this membrane. So that's pretty cool. Now you can write the flux just in terms of the membrane. Diffusion coefficient dE multiplied by Ca bulk. And you can see now we express everything on the macroscope view instead of the pore under the microscope view. Because now you can see the concentration is also written in terms of the bulk part. We are totally talking about what happens on the two sides of the membrane. So you have the inlet concentration, you have outlet concentration. And that's the flux. So there's no need to know what's the concentration within the pore after we do this to do this relation, sort of using the steric factor, the partition coefficient, to link the pore concentration to the bulk concentration. So it's totally a diffusion problem for the membrane. Now, let me introduce like empirically how people estimate omega R. So this is called the Renkin equation. Renkin equation is early on, some scientists like in the 1970s, they sort of did some experiment to figure out the diffusion coefficient across some membrane, and like it's more like a curve fitting. So this is empirical. Empirical from experimental curve fitting. And the Renkin equation says that the K omega R, the product is this multiplied by the other. The first term, we know that it is the partition coefficient. And the second term, which is in the square brackets, is the hindering effect. It is the power to the third. So let me put down this. The first time we know that it is the K. It's the partition coefficient. It's the same K we discussed in the last lecture. And this is omega R. So this works for well, the experiment was coming from a channel with a straight channel with tortuosity equal to 1. Later on, people just use it to approximate the hindering effect. So that's pretty handy. All you need is the ratio of A and R. All right, I think that's all I would like to cover in terms of the lecture content. And I will leave you guys one thought. So consider the diffusion of a vitamin B12 molecules through a synthetic membrane composed of cylindrical pores. The diameter of each pore is 40 nanometer. That's the diameter. And the tortuosity of the pores is given 1.5. This vitamin has an estimated molecular radius and diffusivity in water. And the pores give you the pore length. So this pore length, it's actually the membrane thickness. So this is, let me write it down. This is membrane thickness. The focal concentration of the vitamin at the entrance is given, and then at the exit is assumed to be 0. The membrane has a total surface area, give you the S, and give you porosity. It asks you to calculate the effective diffusion coefficient within the pores. The solute flux through a single pore cross-sectional area and the total vitamin transport rate through the membrane. So it asks you to calculate multiple things. All right. That's the end of the lecture.